Hey everybody, it's Friday, October 16th. As you can see here in the aim today we are starting a new unit, two-dimensional motion. And so our goal today is going to be all about how we can describe motion in two dimensions. Now, as we said yesterday, the video yesterday was really getting into some of these complex one-dimensional acceleration problems, basically dealing with two different objects as they were moving, and that really kind of wraps up one-dimensional motion. Before we fully leave one-dimensional motion behind, though, and get into two-dimensional motion, I want to take a couple of minutes to talk about a lab, because I think it's pretty clear to everybody that a lot of you had issues with the first experiment because getting the data from that kind of experiment was really difficult. And so I just want to make sure that we're all on the same page as far as how the graph works, how it shows you the data you need it to show you, et cetera, et cetera. So one of the experiments you could be asked to design for the AP test is an experiment where you have to measure the acceleration due to gravity. Now, if you remember when we were talking about gravity, the symbol for the acceleration due to gravity is a lowercase g, and there is an equation for gravity. It's called Newton's universal law of gravitation that has an uppercase g, and so that's why I'm always going to refer to the acceleration due to gravity as little g. And so if we are trying to do an experiment where you're trying to measure the acceleration due to gravity, you have to think about which equations would be helpful for you to do that, right? We said the key to any experimental design question is always going to be about which equations can be used. And so obviously here, you want to think about which equations can possibly be used and then pick among them. And so since we are trying to measure the acceleration due to gravity, to me, it makes the most sense to do that just like in a straight up free fall experiment. And in most free fall problems where you have an object, falling down to the ground, being accelerated by gravity, it's dropped, meaning the initial velocity is going to be 0. And so that means the top equation, the final velocity equation, we have v final equals a times t. For the second equation here, the time-independent equation, we have v final equals 2a delta x. And for the last equation, we have delta x equals 1/2 at squared. Now, if we had to ask the question, like which of these equations is different from the others, the equation that's different from the others is definitely the last one. And the reason why the equation at the bottom is different from the last one is you wouldn't actually need to measure any velocities to determine the acceleration due to gravity. Measuring the velocity of an object that has been falling down for a while is kind of difficult. And if you especially want to allow the object to fall over longer and longer distances, then you need more and more complicated equipment, which makes it that much more complicated. And so the governing equation for this experiment, which we've done in class before, as I think I mentioned at some point recently, maybe in a Zoom though, so not all of you heard it, the governing equation for any free fall experiment that we could do, like the experiment that we used to do where we drop water balloons out of the sixth floor window and measure the time it takes for them to fall, is this equation. And as we mentioned, the whole point for this equation is that that equation fits the form of the equation for the slope of a line, delta y over delta x. And so if you take 2 times the displacement and you graph that versus the time squared, that graph is linear. Now, the reason why we want to make a linear graph is because for an accelerating object, like an object in free fall, if you just made a position versus time graph, it would not be linear. And on the AP test, it's a really super helpful framework to talk about making a linear graph because it enables you to hit so many of the points that they're asking you about. So if we graph 2 times the displacement versus the time squared, then the slope here is going to be the acceleration due to gravity. And when the question on the AP test asks you, okay, cool, you've told us the procedure, you've analyzed the situation, and you've told us all the data you're going to collect, how are you going to analyze your data to determine the acceleration due to gravity? All you need to say is, I'm going to plot these numbers on a graph and calculate the slope. The slope is going to be g. Now, what's nice about the experimental design questions is you don't actually have to deal with the annoyance of like a video lab not giving you perfect data because you just talk about how you would measure these things under ideal circumstances, and then they'll give you full credit. So for this problem, essentially what we're trying to say is since we solve for A and the equation says G is equal to the quotient of 2 times delta x over t squared, we can plot the numerator, 2 times delta x, on the y-axis and the denominator, t squared, on the x-axis to get the slope of the graph equal to g. And again, the reason why the slope idea is an important idea when it comes to experimental design is because it automatically forces you to collect data at different distances. So different distances, you collect different times, and now you have a bunch of data points which will help you to eliminate, or I should say limit, the experimental error. Take a second to pause this video and write that down, and when you hit play, we'll actually look at the experiment. Okay, so let's take a look at this experiment. I found like a goofy little simulator online which will allow us to achieve our goals here for this video. So as you can see here, and this is on explorelearning.com, it's one of their gizmos. I'll post the link for you, but unless you make an account, like I made an account, you can only use it for 5 minutes before it expires. And so you can open it in an incognito tab and get 5 more minutes, but once that happens, it's over. I set the dropped item to be a tennis ball, and I made I made it to be no atmosphere, so we wouldn't have to deal with air resistance. Usually when we did this in class, we would do it with an object that was big enough that air resistance wouldn't really be a factor. And so notice when you hit play and you drop it, it bounces. Now, I don't think you can hear this because I'm wearing headphones right now, and the sound is coming through my earphones. But when you drop this thing, it makes like a stupidly loud noise in my ears. I'm not going to lower it a little bit, but you can actually hear it hit the ground, and that's how you know to stop the timer. And so I have a chart made in Excel of the different distances the simulator allows you to go to. Notice it says 1 meter, 2 meters, 3 meters, and 12 meters. So just to go back to that, notice those are the possible distances. And I'm going to measure the times. And because these distances are so small, the times are going to be pretty hard to measure. And so I'm going to want to make multiple trials here. And so I put 5 trials, and then I'm going to average them together in my T average column. Okay. So I'm going to do this quickly, probably a little more quickly than I should, perhaps, but I just want to show you what this would look like when you're going through and doing it. And so let's give it a shot here. Let's measure the first value for the time. And so we got 0.55 seconds. It was a little slow on that one now, so I'll try to be better. 0.50. 0.45. 0.50. Notice actually it was on the bounce back up again, so let's get rid of that one. That was a bad one. 0.45. Just do it one more time. That was bad again. I was too slow. Let's do it again. 0.45. That looks like the one. Okay, so those are my trials for the first one. Now let me just do it one more time and try to let it go to 0.55 seconds. Yeah, it was definitely already on its way back up. So that trial is going to corrupt my data a little bit, but we'll just leave it for now. We'll use it to make a point later on. Okay, so that's it for 1 meter. Let's go to 2 meters. That one was way on the way up, so we'll try that again. 0.64 seconds. Try it again. 0.69. As you can see here, this was on the way back up too, but we're just doing this quickly to try to get some data. We'll talk about how bad our method for measuring is here afterwards. 0.64. And 0.64. Okay, moving on. 3 meters. That was bad. That was bad too. Now, I think it's important to realize as you're going through this, like when you realize, oh, I hit the button too early, or oh, I hit the button too late when you're doing an experiment, you could just say, like, that was bad. Let's get rid of that. 0.83 again. 0.78. 0.78. 0.78. Okay. $12 meters, we got 1.56. Now it's a lot easier to do the time here because you don't have to react so fast. 1.56. 1.56. 1.55. And 1.55. Okay, so now to average these numbers together here, I'm just going to put in the average formula. Oh, it's covered up my thing. So C2 to G2. And boom, now I've got an average. I drag it down like that. Boom, now I've got an average for all of them. Pretty good. Now I'm going to copy these, and you have to be careful when you're copying things in Excel or on Google Sheets, because when you do that, especially when you're using a formula for something, it is going to end up trying to reference the formula to these cells next to it, and there's nothing in there. That's why it said error, divide by 0. And so you have to hit paste and then values only. And this time is a time. And so that would be in seconds. And that really should be here for all of these, because you want to indicate in your work the unit at the top here. That would be an important thing for everybody to remember going forward. And so why am I copying and pasting this? Because remember, you have to have the x variable first and then the y variable, and we have these flipped. But it's also important to realize that I need to do some calculations. And so I'm going to have my x variable first, and that's going to be my time squared, and that'll be in seconds squared. And so I can just use a formula here right quick. I've got my time squared. Of course, we don't want this to be to any more than the number of significant figures that we should have. And then we'll have to double our distance, which is going to be in meters. And so we'll just hit 2 times the distance. And because all of these are supposed to have 2 sig figs as well, because they gave that to us. And so now we just have to graph these. and we'll see what's what. And so we graph them on a scatter plot. Oh yeah, linear graph. That's what I like to see. And then we'll add a trend line. And we're going to display the equation on the chart. And now you have to think, what was the position of the ball, or how much distance had it traveled when 0 time had passed? And the answer is none. So we should be setting the intercept at 0. And when we do that, what do you know? We get a value for the acceleration of 9.8476 seconds. Now, I did this before when I was making the measurements really, really fast, and my acceleration due to gravity number was like 7 point something. And it's important to realize a fundamental point here. When you're doing experiments like this, you want to allow the object to fall for a longer amount of time. And whenever I say that in class, people usually say, oh, is that because of the reaction time? Interestingly enough, reaction time is not really an issue here. And the reason why reaction time is not really an issue here is because if your reaction time is constant, which it usually is, then that means when you're supposed to start the clock, you're delayed. And when you're supposed to stop the clock, you're delayed. And so usually in a normal experiment where you're like actually using a stopwatch, your reaction time cancels out because you're late starting the clock, but you're also late stopping the clock. Now, as was the case for this experiment, because they started the clock for you when you hit the play button, the fact that I was too late made all of my times too big. And now this is a very important thing to realize, because like this is how you're supposed to analyze data from experiments. You can get bad numbers. Your goal is just to figure out why you got bad numbers. And we can figure out pretty clearly here why my acceleration due to gravity was too small. Because if you look at the equation, there is no way that my measurement for the distance was wrong, because that was set by the computer. But the times were measured by me. And now you have to ask yourself the question, what is the relationship between the acceleration due to gravity and the time, according to that equation? And according to that equation, the acceleration due to gravity is inversely proportional to the time squared. So if my times were too big, because it's in the denominator, my accelerations would be too small. And that result actually makes quite a bit of sense. I think the number was like 7.5 or something to that effect. And so if the acceleration is too small, that's perfectly explainable for this type of experiment, because the computer was starting the watch for me. But the fact that I had a reaction time between the time I listened to the sound and clicked the button, my time measurements were too large. And my time measurements being too large makes my acceleration a little too small. Now here, that was not the case, because I knew what the values were supposed to be. And so if you noticed, for some of these times that I measured, I was stopping it. And if you actually looked at the thing, I was stopping it the instant before it hit the ground, because I was like overcorrecting for my own reaction time. But it's important to realize that in a real life experiment where you're dropping things, your reaction time ends up not being all that much of a factor, because it cancels out. Now, you could try to do this experiment on your own at home, but as you'll find, it's actually quite difficult when you're dropping things over the small distances that you'll be able to drop them in your house, because there's going to be uncertainty in any of your time measurements. And as we've said, which is a crucial detail, if you're using small measurements for the distance, like these, then your time numbers are really small. And if your time numbers are really small, then the uncertainty makes up a pretty big percentage of those measurements, which means they're affected more by uncertainty. And that's why this is a good experiment to be doing, because free fall times are pretty small in general. Even when the object is 12 meters above the ground, it only falls for like 1.5 seconds. This is the kind of experiment you want to do where you're able to drop something from very high up in the air. Because the bigger you can make that time, the less your measurements will be affected by the uncertainty in the time measurement. And so that's the idea. Hopefully that's what you were supposed to get out of the experiment the other day. Let me just keep that there, but I want to copy these distance and time measurements for a second. And I'll just draw them onto a new sheet here. Ideally, that's what you were supposed to get for the linearized graph. And for the regular graph, you should have gotten something that looked like this. And if we added a trend line, you should have seen a polynomial fit would work for that. And if we displayed the equation on the chart, now notice it's not perfect, but it's close. The number attached to that t squared term in the position function is 5.2323. Notice if I set the intercept, it barely changes it because my y-intercept was small. And so if we call it 5.23, then when we double it to find our acceleration, we get 10.46. And that would be 10.46 compared to 9.85. 10.46 compared to 9.85. And so if we wanted to calculate the percent difference, we can just use the equation A1 minus A2, the absolute value of that, over the average of A1 and A2 times 100. And so if we did that, we would get 9.85 meters per second squared minus 10.46 meters per second squared over 9.85 meters per second squared plus 10.46 meters per second squared. And we divide that whole thing by 2. And then multiply it by 100. And when you do that math, you get 6.01% difference. So it's important to realize using any experimentally generated data, you're going to get a little bit of percent difference using these two methods of determining the acceleration. And that was kind of the point. I feel like a lot of people missed the point that the whole purpose of linearizing the graph is that it gives you a better way to determine the acceleration because the graph is linear. And finding the slope is a good way to go ahead and do that because we can set the intercept to 0 and all that stuff. And so the 9.85, because you already know what the answer should be, is clearly a more reliable way of determining the acceleration because the linearized graph is a better way of determining a value. All right, let's talk about projectiles. All right, so a decent amount of this is going to be review because we've already talked about projectile motion in the honors class, but because it was something that a lot of people seem to have trouble with when they first see it in honors physics, I hope the refresher that today is going to serve as will sort of help you realize that this stuff is actually not that hard. So obviously here we want to talk about what projectile motion is, right? So projectile motion is motion of an object which is either thrown or projected into the air, subject to only the acceleration of gravity. So we said here that free fall is a situation where objects are only subject to the acceleration due to gravity, and this is a pretty similar situation here. The only difference is that instead of the object just being dropped or thrown straight up, the object is going to be thrown. And so when we talk about projectile motion, when we say the word projectile, we're saying that this really refers to any object that is thrown through the air. Now, I put this last part on there in parentheses, usually in all cases except for when it's thrown straight up, because usually when an object is thrown straight up, we just don't refer to it as a projectile for some reason. It is still technically a projectile. But generally, when we refer to projectile motion, we are talking about objects that are moving both horizontally and vertically. And so, of course, now we have a super important question to ask. And that question is, if an object is moving both horizontally and vertically, how does the motion of the object in the horizontal direction affect its motion in the vertical direction? This is like one of the more important concepts for projectile motion. And of course, we can do an experiment to determine the answer to this question. How does the motion of an object in the horizontal direction affect its motion in the vertical direction? The experiment that we do here, pretty simply, is just taking an object and dropping it next to an object that we launch. And so in this video here, you have this apparatus, and this person is going to load this thing up, and one of the balls is going to be launched, and one of the balls is going to be dropped. And so notice I have this playing at half speed here. I'm just going to bump it back up to normal speed so you can see how fast it is. And when we shoot these objects side by side, you have to notice a very important thing about how they're moving, which you can probably only realize when it's playing slowly. So this person's going to launch both of them. Notice this ball on the left is falling straight down. This ball on the right is being projected. Notice their heights here. And notice which one hits the ground first is the question. And if you watch, you'll notice they hit the ground at the exact same time. And they are always in the middle of the flight here. They are always at the same height throughout their motion. And so because the objects, even though one is thrown horizontally, because they both hit the ground at the same time, we can determine a pretty important fact about their motion. And that fact is the motion of an object in one dimension has no effect on the motion of that object in any other dimension. And so as a result, we say the motions in each direction are independent of each other. This concept is referred to as the independence of motion in two dimensions, and it is one of the most important concepts involved in projectile motion problems. Take a second to pause this video here and write that down, and when you hit play, we'll move on. So if we actually look at where the object is located at each instant, you can see here that whenever we look at the objects, they're always at the same height. And so the basic inference here is that whatever this object is doing horizontally, however fast it's going, that's not affecting what gravity is doing to it to accelerate it in the vertical direction. Now, of course, in the honors class, it's pretty funny because there's always somebody who's skeptical of this fact, and they ask a question and say, like, well, wait a second. You're telling me that if you shoot a gun shoot a bullet out of a gun and you drop a bullet next to it, that they are going to hit the ground at the same time, and they do. In fact, there's a good Mythbusters video, which I'm sure you can find on YouTube, which in which they test this very fact, and they show within a certain degree of experimental error that they do in fact hit the ground at the same time. Obviously, the bullet that's shot ends up really, really far away, right? Instead of looking like this, it ends up looking like this, and it ends up 500 feet away or whatever. But the idea is, however fast it's moving in the horizontal direction has no effect on what gravity is doing vertically. And we can show this one more way by taking a look at another video here. And notice in this video here, this person is going to be explaining a lot of stuff in the beginning, and so I'm just going to be skipping past it. Essentially what he's saying, though, at this point in the video, which you can't hear it, I guess, he's saying there is a spring inside of this cart, and when you load the ball in there, you're essentially loading up the spring so that the cart has that spring launcher in it that's going to shoot the ball straight up. And of course, if the cart was just sitting here and not moving, you would see that if he shot the ball straight up, it would just go straight up and come straight down. And now he's going to take the launcher, and he's saying it's going to be triggered when that card passes a little slot on the cart. And when it triggers, it shoots the ball straight up in the air. And so notice he demonstrates that here. It passes through the slot, and the ball gets shot straight up, and he catches it in the air. And so now he's going to let the thing go, and this is the important part to watch. Let's see that one more time. So notice, when the cart is standing still, the ball goes straight up and straight down and lands in the basket. And when the car is moving sideways, the ball goes up and down and still lands in the basket. And so the only possible conclusion we can have about the motion of that ball in the air is the fact that the cart is moving horizontally. When it is moving horizontally, has no effect on what gravity is doing to this thing in the vertical direction. It's a super important concept for projectile motion. It is the governing concept behind basically everything that we're saying and everything that we're doing. And for today, we are going to apply this concept specifically to one type of projectile motion problem, which we'll call a horizontally launched projectile. If you remember from honors physics, there are essentially two types of projectile motion problem. The first is called, or the first one I call at least, a horizontally launched projectile. The other one I'll refer to as a projectile fired at an angle. And so that is the kind of problem where you'll see the object shot from ground level up at some angle, and it'll look like that. So here for today, though, we're going to just discuss the motion of a horizontally launched projectile. And so as you can see here, when a projectile is launched horizontally, it follows this path here. Let's just pretend that that's straight. I'll take one more shot at that. It follows this path here. This path we call a trajectory. And we can say here that this object has a parabolic trajectory. The person who discovered that the trajectory of a projectile is parabolic was Galileo. And so this is a pretty easy thing to observe. Now, if we have to ask the question of why that is, if you look at the overall trajectory, it looks like a parabola, but it's important to remember essentially what this projectile is doing is it's experiencing two separate motions in each direction. In the vertical direction, this thing is accelerating. Gravity accelerates the object downward. But the whole idea here is, even though gravity accelerates the object downward, because gravity is a vertical force, it is unable to affect the horizontal motion of the projectile. And so here you can, I hope, pretty clearly see that the distance traveled by the object each second is getting larger and larger and larger, and that's because the object is being accelerated by gravity. But in the horizontal direction, the distance this thing travels, as I hope you can see, is the same every second. And so the idea here is, this is a big note, gravity, a force, causes the object to accelerate in the vertical direction. Since there are no horizontal forces acting on the projectile after it's released, and this is true only in the absence of air resistance, the object moves at a constant velocity in the x direction. So before you pause this here and write that down, I just want to say, notice I very specifically use the phrase here, after it's released. And that's because it should be obvious to everybody that when somebody is in the act of throwing a projectile horizontally, they're putting a force on the projectile, right? The projectile is accelerating in the person's hand as they're throwing it, or the projectile is accelerating in the cannon as the cannon is shooting the projectile. But the second the cannonball leaves the cannon, it no longer has that force acting on it, and so the object moves in the x direction at a constant velocity. Take a second to pause this video here and write that down, and when you hit play, we'll talk about how we're going to solve these problems. So notice the parabolic path of the projectile is purely a consequence of the fact that this object is experiencing two different kinds of motion. Those motions don't affect each other, and one of them is at a constant velocity and the other is accelerated. So notice the location of the ball at each specific point is due to the fact that in one direction it's accelerating and in the other direction it's not. And if you literally just plot the positions, you see that it ends up looking like a parabola. That should make sense, though, because the way we get a parabolic shape on a graph is by graphing the function y equals x squared. And so notice the x variable on these graphs is changing by the same amount, or in other words, changing at a constant rate. But the y variable is not changing at a constant rate. It's changing, well, exponentially. It's getting larger and larger and larger because of this squared relationship. And that's what we see for the motion in the y direction, because in the y direction, the distance is not directly proportional to the time. The distance is directly proportional to the time squared. Whereas in the x direction, the distance is directly proportional to the time. And so we're seeing one variable change at a constant rate, the other variable change at an exponential rate, just like we see for an ordinarily graphed parabola. And so the fact that the object is accelerating vertically but not accelerating horizontally is the reason why we have a parabolic trajectory for a projectile. And so let's write here, this is an important note, big note, the trajectory of a projectile is parabolic. This is a consequence of A, the independence of motion in each dimension, and B, the type of motion in each dimension. The fact that the projectile is moving at a constant velocity in the horizontal direction, but is accelerating in the vertical direction, is the reason why the shape is parabolic. Take a second to pause this video here, and when you hit play, we'll move on. So, as I'm sure some of you remember, and even though there are a few of you who did not take honors physics with me, I am quite sure that Miss Neron does, if not the exact thing that I did something very similar. The most annoying thing, in my opinion, about projectile motion problems is just that there's a lot of stuff to keep track of. You have all these different variables in general, right? Like displacement, initial velocity, final velocity, acceleration, time. But now you have two sets of variables, because you have one for the x direction motion and one for the y direction motion. And so the way that we're going to keep track of all these variables is by using a chart. Now, the chart is going to look different for this class than it did for the honors class, because we write the equations a little bit differently in this class than we did in honors physics. The chart is going to look like this. I want you to take a minute to copy this down. The main difference in the chart is that instead of writing the y displacement and the x displacement, we write the x initial position and the x final position and the y initial position and the y final displacement. Now, I'm going to actually instruct you to pause this video here for a second, but I know that some of you are probably wondering, like, why are we wasting our time with that? Why can't we just write the y direction displacement? You will see when we get to harder problems that this will actually be really advantageous, because for certain problems, you'll see that the details are quite complicated. And so if you remember in honors physics, when we did projectiles fired at an angle, we only did these problems on level ground. Now what you'll see in this class is, instead of doing it at level ground, where the object would hit the ground if the ground was flat, there's going to be a hole. And the object is going to continue moving downward into that hole. Or there'll be some cliff, and the object is going to try to be shot on top of the cliff. And so because the ground isn't going to be level for these problems, and it's the same thing for a horizontally launched projectile that we're going to talk about today, the object could end up landing on the ground, but there could be a hole on the ground where the object is going to continue to accelerate. And that means we are going to want to be very careful about determining and writing down specifically the initial position and the final position, because it's not always just going to be like the height of the cliff. And so writing the initial and final positions here are key. Now notice it says, note, we generally assume x naught and y naught are 0, but that is not always the case. If the object stays on level ground, or like for a horizontally launched projectile, if it just starts on the top of a cliff and ends on the ground on the bottom of the cliff, then you can always just say, in this coordinate system, the starting point is what we call x equals 0. But in some cases, it doesn't necessarily pay to do that, is the idea. I want you to take a minute here to pause this video and write that down. And when you hit play, we'll talk about what this chart is going to look like for a horizontally launched projectile. Okay. So next thing I want to do, I know it's annoying that you just wrote down this chart, but I do want you to draw it again, because you're going to have to get used to that. We're going to be doing this every time we solve one of these problems. The chart is going to look very similar for every horizontal projectile problem that you do. And so I think it's a smart idea for us to make a little template chart for what this chart is going to look like for most of these problems. So as we said, for these problems, we're almost always going to call the initial position 0 meters. And I'm going to write in parentheses here most of the time. And that's going to be the same thing for y naught, 0 meters. And so that means your final position, which is going to make your displacement, which is delta y equals y final minus y initial, that's going to make this negative, and that's because the object is going down. And so essentially what you're going to put here in this cell of the chart, or this part, is the vertical displacement. And since that's down, you're going to make it negative. Now, of course, the vertical acceleration here is going to be negative 9.8 meters per second squared. We can also say for sure that the horizontal acceleration is going to be 0 meters per second squared. And that's because, as we mentioned, there are no horizontal forces producing any horizontal accelerations, because the acceleration in the x direction is 0, that means these v naught x and vfx are going to be the same. This x variable is what we're going to call the range. It's how much distance this thing travels horizontally. And as you also may remember from honors physics, these times are the same because time is not a vector. It's a scalar, and it does not differ in each direction. It has no direction. Time is just time. And the last thing we should say is what makes a horizontal projectile problem is that the object is just launched horizontally. And the idea is, if the object is just launched in the horizontal direction, then it's not launched in the vertical direction. And so in the vertical direction, since it's just launched horizontally, the initial speed in the y direction is always going to be 0. And so notice here, because we have to deal with two separate dimensions, we label the x variables x with the subscript x and the y variables y or with the subscript y. And that means we're actually going to use separate equations. Because notice, like the displacement equation, for example, looks like this in the reference table. And that means when we use it for the y direction, we're going to use this version. A slight change, but not that big of a deal. Take a second to pause this video here and copy down whatever of that you haven't copied down, and then we'll go ahead and apply this to a problem. So here's a problem. This is actually in the old textbook for this course. That old textbook was called Jones-Childers. It doesn't really matter to you because you don't have a copy of that textbook. But regardless, it says here, a monkey on a cliff throws a coconut horizontally from a height of 17 meters with a speed of 2.1 meters per second. If the ground below the cliff is level, so they're making this easy for us, if the ground below the cliff is level, how far from the base of the cliff does the coconut strike the ground? All right, so the first thing that we should do is just make a basic sketch of the situation, and then we'll get the chart going. So they tell us here that this monkey is on a cliff, and that cliff is 17 meters high. And they tell us the monkey throws the coconut at 2.1 meters per second. And that's really it. They're asking us how far from the base of the cliff does the coconut land. So making our chart here, make the x column and the y column, and we'll have x naught x, v naught x, vfx, ax, and tx. Of course, we don't need to label that as tx because time is a scalar. And then y naught, y, v naught y, vfy, ay, and t. And so they tell us here that the cliff is 17 meters high. So we'll say almost all of the time that the starting location of the object is the origin of the coordinate system. And so that means that's where x and y are both 0. And so the final position of this coconut is going to be on the ground, which is 17 meters below, below is the important word here, 17 meters below the starting point. And so that means the final position is going to be negative 17 meters. Now, the initial velocity in the y direction is 0, and that's because the problem specifically says the coconut is thrown horizontally. And so because the coconut is just thrown horizontally, the v naught is 0. And the acceleration in the y direction is going to be negative 9.8 meters per second squared. Moving over to the x side, we know that the acceleration in the x direction is 0. We know that the initial velocity of the coconut is 2.1 meters per second. And that makes the final velocity 2.1 meters per second also in the x direction, because the acceleration being the same, The acceleration being 0 tells us the velocity is going to be the same. So now that we have the chart filled out, it's important to realize, I hope everybody realizes, that the chart is useful for two reasons. Number one, because it helps you organize all of your variables, but number two, because it serves as your list of knowns. And that makes this really nice. And so the point here is, once you have the chart filled out, all you have to do when you get to the actual parts of the problem is write your unknown and then just get right to solving the problem. Now I'm going to do this over here before I jump to the next slide just to make a point. The bridge between the x side of the chart and the y side of the chart is the time. And what I mean by the bridge is it allows you to go from one side to the other, because if you find the time on one side, you automatically know the time on the other side. And why am I talking about the time? Well, if you look at the equation for the final position of the coconut, which is the unknown here, we use this equation. Why do we use this equation? Well, it's because the other equations in the x direction don't work. Look, if we use the final velocity equation, which is the same thing as the acceleration equation, we have VFX equals V naught x plus AT, and the acceleration is 0. So that tells us that V naught x is equal to VFX, which is a thing we already know. And if we use the time-independent equation, we have VFX equals V naught x plus 2a delta x, and the acceleration is 0, which tells us VFX squared is equal to V naught x squared. And when we take the square root of both sides, we get VFX is equal to V naught x, which is something that we already know. And so these equations are useless. And so the only equation that works in the x direction, because the fact that the object has no acceleration doesn't kill the whole equation, is the position or displacement equation, however you look at it. And so here, the acceleration being 0 gets rid of that term. The x0 being 0 gets rid of that term. And so now all we're left over with is x equals V naught x times t. And so that tells us to solve for the final position of the coconut, at least the final x position, we need V naught x. Check, we have that. And we need the time, which we don't have. And because this is the only equation that works in the x direction, you can't use it to find the time, because we would need to know x to find it, and that's what we're looking for. So the basic idea for a lot of these problems is using one side of the chart to find the time and then jumping over to the other side of the chart to find the thing you need. And so the first thing we're going to do is we're going to use the y direction information to solve for the time. Like I said, you do not need to rewrite your knowns when you're doing this, because the chart serves as the list of knowns. Because my chart is not on this slide, though, I am just going to rewrite the knowns so we know what they are. We have here y equals negative 17 meters. And it's important to realize also that because delta y, and I'm going to erase this in a second, but delta y is y minus y naught, and y naught is 0. That means delta y is going to be equal to y. And so that means here delta y is also going to be equal to 17 meters. Negative, though, of course. And so you can use this equation, these equations, however you want in terms of the symbols. We have our V naught y is 0, and we have our AY is negative 9.8 meters per second squared. And we're looking for our time. And so the best equation to use with all these variables, incidentally, is the same equation. Delta y equals V naught yt plus 1/2 AYT squared. Notice if you use the quote-unquote position version with the y and the y naught, or you use the displacement version, as I have shown here, it works out to be the same thing. So this term goes to 0, and so we're left over with y, delta y equals 1/2 AYT squared, and solving for the time gives us a square root of 2 delta y over AY. And it's important to realize that that should look familiar. because that is your go-to equation for free fall. And because this object is just thrown horizontally in the y direction, this thing basically is a free fall problem. It has no initial velocity. It's only being accelerated by gravity. It works like any other free fall problem. Yeah, it's moving horizontally, but the horizontal motion has no effect on the vertical motion. And so we plug in 2, then our displacement, negative 17 meters, and then we divide that by negative 9.8 meters per second squared. And when you do that math and you take the square root, you get 1.8626 seconds. And because everything is given in the problem to 2 significant figures, we'll call that 1.9 seconds. Now, as we said, just to wrap this up, we have only one equation in the x direction that works, and that would be x equals x naught plus v naught xt plus 1/2 a xt squared. This term is 0. This term is 0. And so that gives us x equals v naught x times t. And so plugging that in here, we had our v naught x, if you remember, was 2.1 meters per second. And our time here is 1.9 seconds, as we just calculated. And that gives us a horizontal final position here of 3.99 meters, or what we can call 4.0 meters. And that's basically it for this problem. There's not a whole lot to it. Having said that, there are a couple of nice little questions that we can ask here about this situation just for fun. And probably the most significant one is this one. If the monkey was trying to throw the coconut into a basket, at what angle must the basket be tipped for the coconut to strike the bottom? First, we should talk about why that's necessary, right? Because if this thing is traveling over some long distance and there's a basket here on the ground, it's going to hit the side of the basket if it wants to land in the exact center of the basket, because the basket has some height to it. And so essentially what we're saying here is that in order for this thing to strike the basket properly at the bottom, the basket needs to be tipped so that that parabolic trajectory can continue into the basket and the thing can collide with the bottom of the basket. And so now we have to consider what's happening here at the end of the flight. Well, at the end of the flight here, this object has a velocity vector which is pointed diagonally down like this, right? If we are looking at the parabolic trajectory, it looks like this, except a little more curved, I guess. And the velocity is pointed down at some angle, which looks like this. And that velocity, technically, has 2 parts. The x part, which we call VFX, and the y part, which we call VFY. And essentially what we're asking for is what this angle is. Now, I know a lot of you might be looking at that and saying, why is that the angle we're finding? Because if this is the basket here, then if we're finding the angle the basket must be tipped at, then don't we really care about this angle? And the important thing to realize is we have an alternate side, alternate angle, alternate interior angle situation here, so that this angle, which is the angle we're finding, is this angle down here, the angle at which the basket must be tipped. And so by finding the angle on the inside of this velocity triangle, we are finding the angle above the ground the basket must be tipped to. Now for this one, we can just call that like V with an arrow for like the total velocity, or we could put an R for resultant velocity. It doesn't really matter though, because we don't actually need that. What we need is the relationship between this angle the final vertical velocity and the final horizontal velocity. And it's important to realize if this is the angle of the triangle that we're looking for, then this side of the triangle would be the opposite side, and this side of the triangle would be the adjacent side. And so we have to ask the question, which trig function relates the opposite side of the triangle to the adjacent side? And it's the tangent. And so that means here the tangent of the angle is equal to VFY over VFX. And so that means, and I'll just write this over here, to find that angle, we use the inverse tangent of the ratio of the y velocity to the x velocity. And that's our equation. Where, of course, VFY is the final velocity in the y direction and VFX is the final velocity in the x direction, and we already know that. So to finish this one off for today, let's just go ahead and find that angle. We knew from the problem, and I'm just going to write these here just so we have them. We know that V naught y is 0. We know from the problem that this coconut is going to hit the ground in 1.9 seconds. We know, of course, that in the y direction, the acceleration is 9.8 meters per second squared. And we know that the VFX, the final velocity in the x direction, is the initial velocity in the x direction also, which is 2.1 meters per second. According to that equation, to find the angle, we have to find VFY. And once we have VFY, we'll be able to find the angle theta. So first we have to find VFY. Finding VFY here is pretty simple, because if we know the initial velocity, the acceleration, and the time, we can just use the final velocity equation. VFY equals V naught y plus AT. The initial velocity is 0, so we can just get rid of that. And then now we just have to plug in the acceleration, negative 9.8 meters per second squared, times the time, which is 1.9 seconds. And when we do that math and get our answer here, we get an answer of negative 18.62 meters per second, or to two significant figures, negative 19 meters per second. And now that we have VFY and VFX, we can find the angle, theta. And so as we just described in our equation, theta is equal to the inverse tangent of the y final velocity over the x final velocity. And so we just plug them in. We have the inverse tangent here of negative 19 meters per second over 2.1 meters per second. And when you plug those in and you do that math, you get negative 83.69 degrees. And so we'll call that, to two significant figures, negative 84 degrees. And all that negative really means is just that it's below the x-axis. Because notice here, we drew the triangle like that. And so there's our x-axis, and we're just saying that this angle is below the x-axis. Notice it's pretty vertically oriented here. The y velocity is way, way, way bigger than the x velocity, and that's why. So notice if the angle was 90 degrees, it'd be straight down. So really more accurately drawn to scale, it's probably something like that. But that's the idea. You'd have to tilt that basket at 84 degrees for it to hit the bottom. And notice the regular orientation of a basket is that it makes a right angle with the ground. So essentially what we're saying is you just need to slightly tip it so that the angle is 84 degrees for the coconut to go in and hit the bottom. All right, guys, that's it for today. We've reached the part of this problem here where you would then go ahead and do another one and try on your own, and then answer some good conceptual questions about projectile motion. But because this video is getting already a little long for today, we'll stop there. That means for tomorrow's video, we'll have you try one on your own. We'll go over the answers, and then we'll answer some questions on a sheet of paper with some nice conceptual questions related to horizontal projectile motion. All right, everybody. Take care.